Okay, guys. So, as I was explaining yesterday, well, we're starting the new unit, Unit 11, exponential and logarithmic functions. And exponential functions. As you know already, linear functions and like correspond to arithmetic sequences, in the meaning that they are the same, they describe the same type of pattern, but a linear function uses a continuous variable, which is usually x, and an arithmetic sequence uses a discrete variable, independent variable, which is usually n. Same thing happens with exponential functions and geometric sequences. An exponential function and a geometric sequence both describe exponential patterns, either exponential growth or exponential decay, but the difference is that exponential functions use a continuous independent variable, which is usually x, and geometric sequences use a discrete variable, independent variable, which is usually n. Okay, so as I was saying yesterday, this is the analytical expression for any exponential function. F of x equals b times a raised to the power of x. Okay, so let's see what's the meaning of these letters or variables or terms, let's say. Okay, so very similar to geometric sequences, okay? This is an exponential function, and this 10, this b, we can say b is the y-intercept as long as there are no transformations, or let's say um, there are no transformations computed over the function. I will explain this later. Okay, so b is the y-intercept, and let me write this as long as there are no transformations computed on the function. I will explain transformation a little bit later, okay? So, but let's start with that concept, that b is the y-intercept. So it's the point, if there are no transformations, this is going to be the point where the function crosses the y-axis. And we can describe pattern of exponential decay like this. Okay, and you can see that this 10 is common to both, so they both have the same y-intercept. They both are going to cross the y-axis at this point, at 0, 10. Okay, good. You see that, as I mentioned yesterday, if I take these 2, and instead of 2, I write 1 over 2, it's going to be a perfect reflection of the first function over the y-axis. It's like we are reflecting the function over the y-axis. Okay. Here we can see something interesting. Okay. Another characteristic here is that there is an asymptote. Okay. We talked about asymptotes before this year. Okay, let me use the same colors I used previously, like that. Okay, so we know that the asymptote is a line usually that we approach with our function, but we never touch it. Okay, if I get closer, it doesn't touch the asymptote. Okay, same thing on the other side. It doesn't touch it. It gets closer and closer, but it does not touch it. So one important characteristic about exponential functions, even like if it's an exponential growth or if it's exponential decay, it's the same. We are going to have an asymptote, an horizontal asymptote, always in an exponential function. So in the case of exponential growth, we will come from minus infinite with this asymptote, approximating this asymptote, and then we will start growing exponentially, and we will cross the axis at this value, the y-intercept. Good. That's the case for exponential decay. We come from minus infinite, and we cross the axis at the y-intercept, and then we go down exponentially, and we approach the asymptote on our way to plus infinite. Okay. So far, I think it's quite intuitive. Let me, okay, let me explain something about the exponential decay, and it's that there are three ways in which we can express this type of function, exponential decay. It might be obvious for some people, but maybe not for everybody. So this is exactly the same as this. This x in the exponent, of course, it won't affect this type of function written like this, and it's the same. This one, it's okay. But we can also see that written like this. Okay? This is exactly the same. This thing, and this thing, they are exactly the same function. N times 1/2 raised to the power of x, n times 1 over 2 raised to the power of x, or 10 times 2 raised to the power of minus x. They all represent the same thing. Okay? So I'm going to stop recording here for a minute.